guess that's a fair trade. What does it mean?
Do y'all want to turn all the lights off so you can see better, or do y'all want to keep some of them on? Don't matter. I tried to borrow Miss Kill's lamp this morning because it's so dark outside, but it doesn't work. Okay.
Good morning, Grissom High School. Please rise for the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Have a great day, Tigers.
Okay, so for polynomial functions, we're going to first talk about what a polynomial function even is before we discuss like the components on how to graph it or what they are. A polynomial function is used in a lot of areas. It's a math concept that you don't really realize in all the ways that it's used. You've actually been studying polynomials since you were in elementary school, but they didn't tell you that. Like x plus 2, polynomial. Any algebraic expression that contains variables, numbers, where your exponents are all non-negative integers, which means whole numbers, then that would indicate a polynomial. And this is all in your notes and on N2.3. I'm going to go over the vocabulary and concepts with you, and then we'll work some problems that are also in your notes. Polynomial, like I was just saying, is simply an expression that contains variables, numbers, or coefficients, and involves addition, subtraction, all of that. Addition, subtraction, multiplication, division. Some examples of polynomials. If you've got something like negative 3x to the 5th plus root 2x squared plus 5. What you're looking for to see if a function is a polynomial is you're simply just checking all of the exponents. Even though the coefficient of x squared is root 2, I know that looks disgusting, but you're still just checking the exponents of all your variables, which are just 5 and 2. So the exponents have to be non-negative, or you can, of course, just simply say positive. Exponents are non-negative integers, which just means whole numbers. Something that is not a polynomial, you guys, and this is actually what we're going to get to graph in 2.6, is a rational function, which looks like this. And I'll put f of x or y to indicate it's a function. But let's say I've got this function, f of x equals 1 over x. Somebody tell me what your exponent of x really is. When you have x or a variable in the denominator, that actually indicates that you have a negative exponent. So this is really equal to x to the negative 1 power. Do y'all remember that? A long time ago, maybe? So once again, just to check if it's a polynomial or not, check your exponents. Okay, another thing that is discussed with polynomials is exactly like what type they are. The most common polynomials that you've probably worked with are linear or quadratic kind. So what makes a polynomial? A polynomial can simply just be a constant value. It can be linear. It can be quadratic. What's after quadratic? Cubic. So it can also be cubic, and then so on. After cubic, cubic indicates a degree or highest exponent of what? 3. So constant would just simply mean you have a number. Like all you see is a number. For example, you might have f of x equals 2. It's just simply a number by itself. And I know it's kind of weird to think, but yes, like all the numbers in the number system are polynomials. Kind of odd. Linear, tell me the most common type of linear, like you've graphed these so much, starts with an S, slope, intercept. Good, slope, intercept. Y equals mx plus b. So you might have something in that form. An example in numeric form would look like maybe 1/2 x plus 3. Linear just indicates that your highest exponent in your polynomial is 1. Quadratic, somebody give me an example of a quadratic. Maybe like x squared plus x plus 2, something like that, where your highest exponent, of course, is 2. Cubic, same thing, highest exponent is going to be 3. If you're looking in your notes and following along, I put that in very mathematical form. I've got like a f of x equals, for cubic, ax to the 3rd, but we like it a lot better when it's just in simple number form. But that's an example of what a cubic would look like. Of course, a cubic and quadratic, you don't necessarily have to have the x, just as long as your highest exponent's 2, 3, respectively, quadratic and cubic. All right, so just to go back through really quick, polynomials have whole number exponents. So you will never see a variable in the denominator. If you do, automatically not a polynomial. The graph of this is actually broken into 2 branches. And you're going to see in this section that polynomial graphs are all smooth and continuous curves. You don't have any breaks, you don't have any holes in the graphs at all. But when we get to 2.6, those graphs, they will. So that's one reason this is not a polynomial, and this one, something like that is. Okay, how do y'all feel so far? Okay. All right, another thing that we're going to use in a minute to help us graph polynomial functions is the discussion of the degree. And I've actually already been talking about that when we discussed these. Your degree is simply the highest exponent that you have. You're going to see two types of polynomials in all of your problems. So you might have a polynomial that is in factored form, which will actually make it easy on you to find x-intercepts later on that we're going to do. And so that would look like this. You might have some function f of x, like x plus 3 squared, x minus negative x minus 1 to the third power. So in factored form, they're going to have it already broken down for you, like x plus 3. I mean, if you, hopefully you remember factoring, and that does look like it's already been factored out. When it is not, and I'm going to use these ditto marks, just simply means you bring down the word above it to shorten down what we write. So if you have a polynomial not in factored form, it may look like 2x to the 5th minus 1/2 x cubed, something like that. So hopefully you see the difference. One dead giveaway, it's in factored form, you're going to see x plus something in parentheses, x minus something, parentheses. Okay, so the reason I wanted to discuss what this looks like, you find the degrees slightly different. Your degree for a polynomial not in factored form is going to be obvious to you. Like, what's the highest exponent here? 5. So I'll say number 2, number 1. So my degree for number 2, obvious, and it is 5. It's the highest exponent. For the first one, when it's in factored form, you have to find it a little bit differently. So degree for the first one, number 1, what you have to do is look at your exponents of each factored part. Like, what's my exponent for this factored part? 2. And then, like, for example, like if okay, let me back up. Your leading term, which is x, you're going to square that. So I would have x squared here from the first factored part, and then I've got negative x. What's your degree of x here? What's your exponent? Your exponent, okay, it is going to become 3. So all you have to do to get your total degree, take your exponent of x inside, which is 1 here, and multiply it to 2. Take your exponent, which is 1 here, and multiply it to 3. You don't really have to worry about the negative, but and that's all you, then just add that up. Like if you multiplied x squared to x to the third, you would get what? You would get x to the 5th. So that degree happens to also be 5. So when it's in factored form, figure out what your exponent of x is, multiply it to that, exponent, multiply, and then add those two together. Does that make sense? Okay, which we're going to do that. We're going to do that, of course, more in our problems that we work in a minute, because we're going to use that degree. That's going to tell you what your graph actually looks like on the left side and on the right side in behavior. And maybe you remember hearing those terms from Algebra 2 Trig. Okay, your graphs for polynomial functions, and I said this a minute ago, And you can think about different types of polynomial functions that you've already graphed. They are always smooth, which means you will not have any sharp edges. For example, tell me what's a graph that you know of like comes to a very sharp point. You graphed these at the first of algebra 2 trig last year and hated it. Absolute value. And that's what they just got through doing. They're smooth and continuous. So for example, like absolute value graphs are not polynomial functions. So a rough sketch of a polynomial function, a very common one that you've been graphing is y equals x squared, which of course forms a parabola. Here's another one that you graphed last year, like y equals x cubed. That's a polynomial function. They're just smooth and continuous. One we're going to graph today kind of looks like the McDonald's sign. So we're gonna figure out where they cross the x-axis, and we're gonna use that to help us graph it. We're gonna figure out also the y-intercepts, and the leading degree and the leading term and degree will tell us what it's doing on the ends. So those are polynomials, and then not a polynomial would be something like if you graph a curve, but let's say it would have a hole in it. Your graph cannot have a hole, and it cannot form like sharp edges. All right, so really quick, let's talk about in behavior while we're on exponents and degree. This is actually on page 2 of your notes. Okay, we're going to use in behavior is going to be one step of our process to graph them in a minute. What you need to know is that even degree polynomials have the same in behavior. Same in behavior. Odd degree have the opposite. So let that, like odd, opposite, both start with O. Let that be a way to help you remember it. So even degree polynomials, they're either going to go up on both sides, or it's going to go down. And odd degree, of course, it's either going to go up on the left, down on the right, or vice versa. All right, and what we use to help us determine that, well, I'll first show you like a rough sketch. Let's say that you've got y equals x squared and y equals negative x squared. Very basic, common polynomial function that you know. Of course, you know that y equals x squared would be a parabola going up. And then negative x squared would just mean it is flipped down or reflected across the x-axis. And of course, we can see obviously that my degree for both polynomials is 2. So it's an even degree. So if your degree is 2, you're going to see, we're going to graph actually an x to the 4th polynomial in a minute. That's the one that kind of looks like the upside down, well, the McDonald's sign, or it's flipped. Common odd degree is y equals x cubed. And the rough sketch of it looks like this. That's if your leading degree, notice, is +1, and it's going down on the left side and it's going up on the right. It is just exactly what you would think. Down, we would associate with decreasing, left, also on the number line, right, increasing, going up. So when your leading coefficient is positive, up, right, left, down, up, right, left, down. If your leading coefficient is negative or you have a negative sign out front, it's just going to flip it or reflect it across the y-axis in this case, if it's odd degree. And it would just reverse, of course. You'd be going up on the left side of it, and it would be going down on the right side. All right, we're just going to look at a few. This is actually in the middle of page 3 in your notes. This is the example 2 that I have. It says use the leading coefficient test, which means you find your term with the highest degree. Look at the sign in front of it. Degree is even. If the number is negative, down, down, and so on. So use leading coefficient to get end behavior. So I give several different examples in this. I'm not going to go through every single one of them with you, but I've got this sum function f of x equals negative x to the 4th plus x squared. What is your degree? The degree is 4, so we know that it's either going up, up, or it's going down, down. And this is your leading term. This is my highest exponent. So this whole chunk is my leading coefficient or leading term. Leading coefficient is actually -1. So it's negative, so it's going to go down on the left side, down on the right side. MathLab may state it as it's rising or falling. So of course you would just say it's falling on the left side, falling on the right side. Another way that you can check these is, of course, just typing those into Desmos and seeing what it looks like visually. Okay, how do y'all feel about that? Are y'all okay so far? All right, so part B, I'll give you one that is in factored form already. So we've got -3 out front, x plus 5, x plus 2, and that is squared. Okay, so when it's in factored form, you have to go through every factor that contains a variable. So I need to look at this one, look at what it's raised to. So what's your degree here total? Good. Your degree is total of 1 for that particular part. My exponent of x is 1. My degree, it's raised to the second power. So what's your degree for this part? 2. So my degree total is 3. You just add those together. So my degree is 3. So it's odd. So I know it's going to have opposite end behavior, but I have to look out front to see if it's either going to go down on the left, up on the right, or vice versa. And of course, we see a negative leading coefficient out front. So this will be what? This is going to go good. It's going to go up on the left side and it's going to go down on the right. It's different than what you think. So the negative sign, we don't like negative things in our life. It flips us out. So think about it like that. Negative, when you have a negative with these, it's opposite of what you think. Okay, one more quick thing to talk about, and then we're going to actually graph some, and then is the x-intercepts and what that tells you. So now we know how to use the leading coefficient. We're going to use that in behavior to help us graph. The next part, we're also going to find the x-intercepts for every polynomial and use the behavior at that point on the x-axis for us to sketch our graph. This is at the bottom of page 3 in your notes, finding roots, solutions, x-intercepts. And if you need a refresher on factoring, well, this is the lesson for you. And if you don't like factoring, then maybe you'll get better at it after this. X-intercepts, they tend to call zeros, roots, solutions, but all those just mean x-intercepts. If you see any of those 4 terms, roots, zeros is really the most common one that they use. And the reason they do that is because in order to find where these graphs are going to cross the x-axis, you have to set y equal to what? If you're good, you have to set y equal to 0. If you're on the y-axis, if you're on the x, your y is equal to 0. So just like when you solve a quadratic equation, you're finding the roots because the quadratic, you have to set it equal to 0 to solve. And what you're essentially doing is just finding the x-intercept. Okay. You have 2 possibilities. Like if you factor, because that's what we got to do first, factor it if it's not already factored. I was trying to think. I think in some of these, if it don't factor and it's quadratic, you may have to use quadratic formula to find the zeros or solutions. So those problems get very fun. So factor and set each factor equal to 0 to solve for that particular x-intercept. Unless it's already in factor form, then they make it easy on you there. Okay, when you find your x-intercepts or zeros, there's 2 possibilities. You can have an even multiplicity or an odd multiplicity. And all that means is how many times you see that particular factor. So for example, I'll show you what one looks like with an even multiplicity. If I factor something and I wind up with this, like x plus 4 times x plus 4, like I see that the same factor occurs how many times? Twice. So that, of course, is an even multiplicity. Another way that you could also see that written is x plus 4 squared. So those are examples of what an even multiplicity would look like. Or you could have x plus 4 to the 3rd and then times x plus 4 to the 1st. That would be, of course, a 4th or even multiplicity. What this indicates is at -4, which would be your x-intercept or 0, your graph is actually going to touch the x-axis and turn back from wherever direction it's coming from. So we would say it touches and turns back. So that's why we find the x-intercepts and then their multiplicity. I'm going to find the point at which the graph either touches and turns at the x-axis or either where what do you think it would do if it's an odd multiplicity? Good, it would cross. And you, do you guys remember this a little bit from algebra teacher week last year? Last year, it was the first time you saw it. So I know it overloaded mine when I taught them. So hopefully this year when you see it again, it might be a little bit different. So example of an odd multiplicity, let's say I'll throw in a 2 just to make it interesting. So let's say you got 2x minus 1, and then you see 2x minus 1 squared. Then of course that would be an odd multiplicity, because another way you could rewrite that all together is 2x minus 1 cubed. It's going to cross over the x-axis at that. This one would be positive 1/2 would be your x-intercept here. So even multiplicity, it's going to touch and turn wherever it's coming from. If it's coming down to the x-axis, it's going to turn back and go up. If it's coming from underneath the x-axis, it's going to touch the x-axis and turn back down, or it's going to cross over to the other side. Okay, do you guys remember in chapter, I think it may be 1.3, it was in unit 1, 1.3, we discussed symmetry. So in math lab, they ask you for symmetry to figure out if the graph would have symmetry with the y-axis or x-axis, and this is the way you do it. If you plug in, well, let me back up. If you plug in, does anybody remember how to check symmetry algebraically? Okay, plug in negative x for every variable. If you get, okay, if your answer is the original function, then it is an even function, and it's symmetric with what? It's symmetric with y-axis. Even, it's going to be symmetric with the y-axis. So that's a way for you to check, is just go through and plug in negative x. But I'll show you how to like really do that mentally and not really have to show any work. So anyway, even if you plug in negative x, get the same original function out all the way through, like no signs change, nothing, then it is going to be symmetric with the y-axis. So that's another way you can double check if you graphed it correctly. If your answer is completely opposite, like every single term in that entire function has to change signs. So if my answer is completely opposite, like all my signs change, then your graph is odd, and that's symmetric with the origin, which would actually, I'll show you the graph of x cubed. That one has origin symmetry, which we've already looked at. So just refer back up to your notes up the top, and you can see y equals x cubed. If it's in opposite quadrants or diagonal quadrants, that's odd symmetry. Okay, one last thing before, well, let's go ahead and graph them. Let's go ahead and graph all the information that we have. Well, okay, no, one more thing. All right, really quick. It's just simply, we're also going to find the y-intercept. So just to review really quick, we're using the end behavior. We're going to find the x-intercepts. We're going to use symmetry. And then we're also going to find the y-intercept. How do you find the y-intercept of any graph? Good. That's all you're going to do is just plug in 0 for x and solve. Most of the time, you will be able to easily see your y-intercept. So you really won't have, this part shouldn't require much work at all. So plug in 0 for x, and we're going to plot that. We're going to plot our x-intercepts, use in behavior, use the multiplicity of zeros to do a rough sketch. All right, so here we go. And I'm going to go through the steps of how to graph it with you as we are doing one. This is example 5 in your notes. They tell you to graph, and then MATLAB is going to tell you to graph using 7 steps. But I'm going to go through all of that with you. It will look like a lot, and it kind of is, but each step is really not too terribly bad unless you have to use quadratic formula. So we have x cubed plus 2x squared minus x minus 2. Okay, my very first thing that I want to do is just figure out what it will look like on the left and right side. I want to get that overall general in behavior, and then I'm going to start working towards what does the middle part of my graph look like. So first step, in behavior. And you use your leading coefficient test. So first of all, is this in normal form or is it in factored form? It's definitely normal or standard form. So when we find our x-intercepts, we're going to have to factor it. But anyway, we'll get there in a minute. What's your highest exponent? What's your degree? 30. Is your leading coefficient positive or negative? Good. It's degree 3. It's positive. So this graph should be doing what? Down left, up right. Can y'all see me okay, or do I need to zoom in? Okay. And then we'll zoom back out to graph it. All right, step 2. Now that we know what it looks like on the outside, I'm going to start examining my middle behavior. And the second thing is find your x-intercepts or your zeros. So this is where all the factoring rules come into play, quadratic formula, if we need to use it to find x-intercepts. Notice this polynomial has 4 terms. And do you remember how to graph something in that form? Need to factor it by grouping. Yeah, fun times. So we have to factor, you don't have to write this down. I'm just going to write it. And all right, factor by grouping. all you do is group two things together that have something in common that you can pull out. These two would have, if I leave them as they are and choose to pair these two together, what can I factor out? Good, so I can factor out x squared from that first part. And you don't have to write f of x if you don't want to. All right, so let's factor out x squared from the first part, and I will be left with x plus 2. So if I pull out x squared, left with x plus 2. Should have left some middle room right here. And then the second, when you factor by grouping, you're going to have plus or minus something here, whatever you pull out from the other pair. So from this, what's the only thing I can factor out? -1, and you're left with, my goodness, x plus 2. Left with x plus 2 there. And that's what we want. When you factor by grouping, you want the same thing inside parentheses left. So then how you write your final answer when you factor it, you take what's left on the outside, which would be x squared, and then what would this be? -1, and put it inside one parenthesis, and then you put what they have in common in the other parenthesis. All right, so we had to factor it first and do some groundwork there. Let's figure out what my actual x-intercepts are and what their multiplicities are. So I should have put that up here. So multiplicity as well. All right, if I take x squared minus 1 and set it equal to 0 and solve, take x plus 2, set it equal to 0 and solve, you would add 1 to the side, of course, and then you have to be really careful when you have x squared equals something. A very common thing people forget is to put what? Good. So you're going to have plus or minus 1 when we take the square root of both sides. So you actually have 2 x-intercepts. And another dead giveaway that you have 2 x-intercepts from this is that x was squared. So there's going to be 2 roots or 2 x-intercepts with just that part. And this, of course, you don't even have to show that work. I mean, I know some of you can do that in your head, and that's fine. So I'm just going to bubble those in. I'll need those in a minute. There's all 3 of my x-intercepts. Another way that you know you should have 3 is because your highest degree was 3. All right, next thing, let's figure out their multiplicity. How many times do you see positive 1 occur? You only see it occur once. When you have something like this, x squared equals a number, and you solve, both of those would have a multiplicity of 1. So x positive 1 and -1, multiplicity of 1. So that's odd. So your graph should do what at both of those points? Cross. And then this also had a multiplicity of 1 because you just see x plus 2 one time and its degree is 1. So this is also going to cross at that point. Okay, number 3, let's find the y-intercept. We're almost done, and then we're going to graph it. So y-intercept, I told you that you should be able to see it easily. Set x equal to 0. And I'll go back up to the original. All right, let me go back up here. When it's not factored, you should be able to tell your y-intercept easily. If I plug in 0 for x here, here, and here, that all goes away. So what are you left with? Left -2. When it's not in factored form, look at the number at the end, the constant by itself. If there's not a constant by itself at the end, then what would it be? Good. If I didn't have -2 there and this is all I had, then my y-intercept would be 0. Okay, so I can easily tell that my y-intercept is 0, -2. Last thing that you have to check for is symmetry. And then we're also going to talk about turning points, which I forgot to tell you about before we did all this. But turning points is easy too, like that. Number 4, symmetry. We're just trying to see if it has symmetry or if it doesn't. And this is where you would plug in -x. But if you know, like, think about this common sense, and hopefully you guys know this by now. If I take a negative number and square it or raise it to an even exponent, what's always going to happen? It's always going to be positive. If I take a negative number and I raise it to this third power, what happens? If I've got like -1 times -1 times -1, I get what? I get -1, so it changes the sign. So if I plug in -x here and raise it to the third power, then this is going to change the sign. And remember, it has to change the sign of everything throughout in order for it to be odd and have origin symmetry. It has to all stay the same in order for it to be even or be symmetric with the y-axis. So if I go through and plug in -x, just do that in your head. Like, does my sign change? Yes or no? Does my sign change? Yes or no? You know, so on. If all of your signs change, then even. If all of your signs change, it's odd. If all of them stay the same, even. If some change, it's neither. Are y'all okay with that? So sign will change, sign will not change. So you know right then what? Good, it's neither. So it doesn't have symmetry with the y-axis or the origin. So it's neither. Okay, finally. All right, let's go back and sketch it using everything that we found. We know it should go down on the left, up on the right. Let's plot our, the first thing we want to do in step 2, plot all of your x-intercepts that you found. And then we're also going to plot our y-intercept. So x-intercept we found was +1. We found one to be -1. And we also found an x-intercept of -2. And then your y-intercept was -2. So you're really to graph it, you're using just your x-intercepts, y-intercept, and behavior. All right, this is the way you use your end behavior. You start at your farthest left point on your graph, which would be this one. And you either draw part of it going up from that point, or you draw part of it going down from that point. I know it should be going down on the left side, so and this is a rough sketch. So for all of you people that like to be very accurate, this is not gonna be your favorite thing. Now, what you're trying to do to see what it's either going to cross and come back to this point, or it's either gonna bump down and come back up to that point. And we already determined at like all of our x-intercepts, it's gonna cross. So all you do is just a rough sketch. You can go up as high as you want, but it's gonna cross at this x-intercept, come back down to this one. It's also going to cross through that one, and then make sure that one comes to your next point, which is the y-intercept. And it's going to come back up, and it also crosses through that graph. If you get your multiplicities right, then when you graph that other side, it should match up with your end behavior, and it does. And then, of course, as you can see, it definitely doesn't have any symmetry, which is what we did find. Okay, how do y'all feel about that? Okay. Yeah, go ahead. All right, one more, we'll craft one more together and then I'll let you guys have the rest of the time to work. I'm trying to find, we'll do one that's different. All right, I'll say this is number 2. It's gonna say graph using 7 steps. I'll call this one g of x. Okay, first thing, let's figure out in behavior. What is your degree? Okay, y'all said that like in perfect unison. Degree is 4, and then your leading term is negative. So this graph is doing what? Down, down, good. Even's gonna go up, up, or down, down. All right, number 2, your x-intercepts or zeros are very easy to find. No factoring involved since it's already factored. What would be your x-intercept for this piece? For the x plus 1? You've got, good. So for that piece, and I'll just write them. So you've got x equals -1. What's that multiplicity? Good. So it's got an even multiplicity, so it's going to touch the x-axis and turn back. Touch and turn. And then for this piece, when you set that equal to 0 and solve, like just do it in your head, add 4 and then divide by 2. So what's your x-intercept here? Good. So for those of you that need to see that, like just set it equal to 0, solve, divide by 2. So x equals 2. And then what would that multiplicity be? That multiplicity is also even. So it's going to touch and turn back. Okay, third thing, let's find the y-intercept. Okay, so the x-intercept and y-intercept kind of switch roles here. When it's in factor form, you actually have to do more work to get your y-intercept. In the factor form, you have to plug in 0 for x. I mean, you can still do it in your head, of course, but in all of these, I always just go through and plug in x into my original. I mean, plug in 0 for x. So I plug in 0 for x here, and I plug in 0 for x there. That leaves you with -2 times, you're left with 1 inside, and then I'm left with 0 minus 4, which is -4 in that spot. I see people mess up on this simple math all the time. Tell me, what does order of operations say to do first in that? Good. You have to do exponents, and you'd be surprised at how many people want to go ahead and multiply -2 to 1, then square that. So please be careful. You do the exponent parts first, then all of that is still multiplied together. So I've got -2 times 1 times 16, and then I multiply that together. Good grief. -32 is my y-intercept there. I could have picked a better one. They're always bad when I make them up. So -32, 0, -32, which of course you can go by 2's on your on your y-axis, whatever. Number 4, let's figure out symmetry. Since they have you practice that again. Once again, that's where you plug in negative x. All right, let me go back to the top. If you take negative x and plug in, and then you're squaring all of that, do you think you're going to get a sign change, or you think it's going to stay the same? It's going to stay the same. And of course, the same situation here, because I have degree of 2. If one, and then, so it's going to stay the same. And so it should be even, should be symmetric with the y. And we'll see if it is. All right, let's go back. This goes up to 15. My graph does. It's a 15 by 15. So I'm just going to go by 2's on my y-axis to take into account that y-intercept of 32. So I'll put a mark up here. I'm going by 2's on my y-axis, so that will be 32. Let's graph the x-intercepts, -1. Graph the other x-intercept of 2. Your y-intercept is 32, -32. So sorry. So it's way down here. Okay, what did we say? Once again, start on the farthest left point, and then your graph should come to this point or past to this point, and then it's going to come to this next point, then last but not least this one. It should be going down through this point, and it should be going down through this point. So I told you, start with your farthest left, use your end behavior, either going up or you're going down. So you can draw a curve coming down from that point. Is your graph going to cross the x-axis or touch and turn back down? It's going to touch and turn back down, and it has to pass through this y-intercept because that's the next point that occurs. And then, of course, it has to come back up, touch, go through this point. Try to make it curve too as much as possible. Like I tried not to make mine come down and like do a V, but it's kind of hard to. And then, of course, we know from this point it's going to touch and turn back down. I should have curved that a little bit more. But as you see, they're rough sketches. So as long as, like, the main thing, especially if you're doing this on paper, and you can see mine's definitely not the prettiest, but I would check to see if your x-intercepts are graphed correctly and y-intercept. Check to see that your end behavior is correct, and that, like, just check overall to see. Okay, how do y'all feel about that? All right, so you can use this time to work. I want to show you one. I'm not going to go through this one, but one like this, just make sure you remember how to factor that. Just pull out what they have in common, which would be that negative. I would go ahead and factor out the negative x squared, and then you would be left with difference of squares, x squared minus 16, which would factor in the x plus 4, x minus 4. So just look out for that part with factoring, but everything else works the same. Okay, so use this time to work.